example, many of you have had glycolysis with other classes. Glycolysis in humans is identical to glycolysis in bacteria. There is no difference between what we do and what the bacteria do. We got it from the bacteria. But the thing is, by studying bacteria first, it's much simpler, much easier, and then we can apply whatever information we get from the bacteria to humans. We go the easy route and then we apply it to the more complicated. Antibiotics. You've all heard that old saying, know your enemy. Well, in this case, bacteria and disease is the enemy. Somebody's got to make up all those antibiotics and all the drugs and stuff. Well, by studying bacteria, by learning how they operate, we can learn how to make them not operate, which is the whole point. So like I say, antibiotics are not made by magic. Somebody's got to figure out how to do that, and that comes from studying microorganisms. Commercial uses. In this, there's a million. Oil spills. Bacteria have been developed that can eat oil. Now, you get the giant oil slicks. Bacteria cannot eat that. There's too much oil. Well, what's done is the giant oil slicks might be several miles wide on the ocean, and the bacteria will be dropped down from planes. And they will basically, the bacteria will eat swaths, eat pathways through the oil slicks. They'll break up the oil slicks into smaller patches. And the smaller patches will be broken up by tidal action and wind action. Much easier to break up several smaller pieces, maybe 50 yards wide each, than a single oil slick that might be 3 miles wide. So bacteria have been developed to basically eat oil to some extent. Yogurt, buttermilk, stuff like that, of course, has been used for centuries with bacteria. Genetics. Much of our genetic information has come from bacteria. It's the same idea as what I said up here with metabolism, that the general processes are the same. So essentially, we study the bacteria, we learn how the bacteria do genetic action, and then we apply it to humans. Take the easy route, and then make it more complicated with the mammalian system. Now, an easy example of what I'm talking about is, now again, I know that many of you have already had genetics somewhere else. You may have forgotten it, but you've had it. So you may remember an enzyme called DNA polymerase. DNA polymerase helps to make new DNA. Well, bacteria have a single DNA polymerase. Humans have 3. Now they do the same thing, they make new DNA. We have 3 different enzymes that can do the same thing. Bacteria have 1. Now just an example of how our system is more complicated than the bacterial system, even though ultimately it's doing the same thing. And we will be doing genetics later in the course. So that's kind of why you're here, so you can learn all that stuff. Now, brief history. What has gone on before us? Robert Hooke. Robert Hooke, 1665, was an Englishman. And he saw the first cell. It was right about then, 1665, that the microscope was invented. So obviously people were seeing things they had never seen before. And he saw the first cells in a piece of cork. And he saw these wide open spaces. And just as an example of how much times have changed, when he saw these wide open spaces, he called them cells because they reminded him of the cells of a monastery. Now, how many of us would actually have any idea what the cells of a monastery look like? And I'm sure none of us. But apparently back then, everybody did. So We obviously still use the term cells today, but it came originally from cells of a monastery. But Robert Hooke did that. Now this one, I've always wanted to make a bet with my students. I've never had the nerve to do it. And the bet is, if you can pronounce this guy's name, you get an A for the quarter. I've always had a... Okay, you lose. Who else?
Van Leeuwenhoek.
Almost. Van Leeuwenhoek. Van Leeuwenhoek. The EEU is pronounced like an A, the W like a V, and the HOEK is just pronounced like hook. So Van Leeuwenhoek. Dustman. Dustman. Now a dead dustman, but still a dustman. And so he was 1675, about the same time span. And he did the classic experiment, of course, classic, he was the first one, of looking at pond water under a microscope. And he saw little microorganisms. He called them beasties. Beasties. Because back then, they'd never seen such a thing, never even dreamed of it. So he saw the first microorganisms.
So I'm sorry, how did Hooke first see cells under a microscope, right?
Robert, oh yeah.
Okay.
Yeah, Robert Hooke was looking at a piece of cork under a microscope. And Van Leeuwenhoek was looking at pond water under a microscope.
From a piece of cork, you said that saw?
Piece of cork.
Like cork in a wine bottle cork?
Yeah. Cork. Spontaneous generation. Notice the question mark.
Is that what they thought?
Spontaneous generation is living organisms coming from non-living things. That is spontaneous generation. Living organisms coming from non-living things. The question mark is it true or not? They were trying to find out. Now today, we would say, no, it is not true. We do not get living things coming from non-living. None of us came out of a rock, that kind of thing. But back then, they didn't know that. They were trying to find out. So this guy, Redi, Francisco Redi, an Italian, 1668, all about the same time span. Now the microscope came out and it just triggered all kinds of research and stuff. Redi was trying to disprove spontaneous generation. He was trying to say no. So his experiment, he put meat into 3 sealed jars, meat into 3 open jars. Only the open jars developed maggots. Well, he was criticized, and that's not a bad thing. You know, he was criticized because the sealed jars did not allow any air in. And the comments were, if there's no air, how could you develop life? Fair enough comment. So he did it again. This time, to allow air in, he covered the 3 covered jars only with gauze. So a netting. And the net would allow air in, but no maggots. And so he still got similar results, but it did not convince anybody. So the argument continued for 200 years. Until Louis Pasteur, a Frenchman, 1861, so it really was about 200 years later. He is given credit for disproving spontaneous generation. So he made this glassware, this flask with a very long curved neck. And the flask contained boiled broth, a meat broth, boiled meat broth. So being boiled, it was sterile. And then this long curved neck was was not just long and curved, it was also covered with a sticky material. The idea was it was open to the air so bacteria could come in, and by that time they were completely aware of bacteria. Bacteria could come in, but somewhere along the way it would get stuck. And by the time it got here, it didn't get there. Bacteria would not be able to reach the broth. So even though it was open to the air, nothing ever developed. No mold, no fungus or whatever. Nothing ever happened. That was the proof that living things can only come from other living things. This was non-living. This was non-living. It was oil. And nothing ever grew. Now, it turned out that Louis Pasteur was quite a guy. He also helped save the French wine industry. Now, I'm sure many of you are aware the French drink a lot of wine. The Germans drink beer. The British drink warm beer for some ungodly reason. And they do. And the French drink wine. But apparently, right about this time, in 1860 or so, the French wine industry was going under. Now, the French have produced wine for centuries. And apparently, well, what Pasteur found is that the yeast used to make wine would convert the sugar in the grapes into alcohol, into fermentation. And that would be the wine, but only in the absence of air. Only in the absence of air. In the presence of air, the bacteria change the alcohol into vinegar. You would take your date out for a romantic evening and you'd give her a glass of vinegar. It didn't go well. And the French wine industry was going under. So anyhow, basically Pasteur discovered this thing with the alcohol and the vinegar and the air. And he told the wine people, you need to get new equipment. Because I'm sure a lot of that stuff was centuries old. They were doing it the way they'd always done it. And I can certainly visualize these people saying, no, too expensive. Sorry. And Pasteur would say, fine, they keep making vinegar. So they really had no choice. They had to either get new equipment or they would go under. So they did. And of course, we still have French wine. As you might guess, pasteurizing of milk came from Louis Pasteur. He did quite a bit. He was a busy guy. Joseph Lister, same time span again, 1860. He was an English doctor. The first one to do disinfecting. Up until then, surgeons everywhere would take their knife, they'd cut you open, and do whatever they were doing, and then wipe off the knife with a towel and go on to the next person. That's how they did it. As you might imagine, a lot of the patients died from the surgery, not from whatever was wrong. And so Lister started disinfecting. He would boil his instruments, and he also used carbolic acid, which today is called phenol. And I remember reading that the other doctors at the time would laugh at him because he was doing all this extra work for nothing. You know, why do it? But as you might imagine, even though this is all fairly crude by today's standards, it was way ahead of what the other doctors were doing. So very quickly, it was found that Lister's patients were surviving a lot better than the other patients. So obviously, they all started doing it, and today we do a lot more of it. But Lister was the first one, started disinfecting his surgical instruments. Robert Koch, the guttural, because he's German. And this is around 1900 or so. This guy is given credit for the molecular model, the bacterial model of disease. The bacterial model of disease. Now, what that means is he's the one who actually proved that bacteria can cause disease. Now, let me make a comment about that. He was not the first one to come up with the idea. It had been speculated for a long time that bacteria cause disease. It's quite common when somebody actually proves something, when he's given credit for something. He was not the first one. Usually it's been around for a while, but nobody had proven it yet. He proved it. A better example would really be Charles Darwin. You're all familiar, of course, that Darwin is given credit for evolution and so on. The idea of evolution had been around for a couple of centuries. He was not even close to being the first one to think about it. So, for example, everybody knew about dinosaur fossils and so on. They couldn't really explain it because everybody believed in creationism at that time. But they all knew about it. The idea of evolution was not a new one. But Darwin has always been given credit because he proved it. I know a lot of people today say, no, yeah, don't want to talk about it. But for most scientists, evolution is not a theory, it's just a fact. And Darwin's the one who actually came up with the actual proof that it is a real thing. But he was not the first. And Koch also was not the first. He just simply came up with the proof. And in this case, he took bacteria, basically took a blood sample. Took a blood sample from cattle with anthrax. Anthrax is normally a cattle disease. But we can get it too. It can spread to humans. But it's normally a cattle disease. And he took a blood sample from sick cows, injected it into healthy cows, and as you might expect, those cows got sick. And then when the cows got sick, he took out a blood sample and he found the same bacteria. And I know you're going to think, well, of course he found the same bacteria. He just put them in. Yeah, but they had multiplied. There were a lot of bacteria. And the cow got sick. So that was the proof. So again, he's given the credit for proving the bacterial model of disease. Proving that bacteria can cause disease. By the way, all of this stuff might appear on the quiz next week. In fact, count on it. What you need to know are the names and simply what they're famous for. Like, for example, Robert Hooke saw the first cells. That's good enough. Saw the first cells in a piece of pork. You don't need to know any of the details or the year. That's not necessary. I'm just saying here, Koch, the bacterial model of disease. You don't need to remember the details about the cows or the anthrax. So just know the name and what they did, what they're famous for. One more here, Edward Kennard, another English doctor, 1798, so almost 1800. Now, he did the first vaccinations. Now, I actually should back off from that. He did the first systematic vaccination. Once again, he was not the first one to come up with the idea. But nobody quite knew how it worked, and nobody quite knew why it worked, et cetera, et cetera. But kind of an interesting story on this one. Jenner was, again, a doctor in London, and at this particular time, 1798, there's a terrible smallpox epidemic going around Europe and around England. And smallpox, fortunately, is something none of us has ever seen, and hopefully never will. It's a terrible disease. If you catch smallpox, the best you can hope for is you would survive with a disfigured face. Your face would be all carved up and stuff from the smallpox. Probably you die. It's a bad, bad, bad disease. At any rate, nowadays we don't have it anymore. Back then they did. And so Janet was working with the smallpox epidemic and stuff, and one day decided to go out into the English countryside, take a break, and go out into the countryside and just walk around and recharge himself. And he met up with this English milkmaid who was walking a cow or something, I don't know. And he was talking to her, asking her if she was worried about the smallpox epidemic. And she said no. No, she'd already had cowpox. She'd already had cowpox, which is a more mild version of smallpox. It's a mild version of smallpox. And her comment was, everybody knows that once you've had cowpox, you never get smallpox. Well, maybe everybody knew it, but Edward Jenner did not know it. And the sorry. And the British Medical Association did not know it. So he tried it out. And he took some scrapings, so some tissue samples or some blood samples from cowpox victims, maybe the milkmaid herself, cowpox victim, and then injected it into a couple of volunteers. And sure enough, those volunteers, they did get cowpox, but they never got smallpox. So he's credited with the first vaccination. The thing that I credit him with is he actually listened to the milkmaid. You know, I've always wondered in myself, if I were in that position, would I have listened to her? I'm pretty sure I wouldn't have. You know, essentially it falls into the category of folk medicine. And I'm sure many of you know that a lot of folk medicine is very, very good. It works. A lot of it's really stupid. So you have to kind of pick and choose. But he actually listened to her. I'm not sure I would have. And he listened to her and he took action. And again, developed a systematic form of vaccination that we still use today.
I mean, it's logical.
So, what degree was like cowpox? Because the smallpox would like deteriorate your face. Well, cowpox.
Cowpox is actually kind of like measles or something, or chickenpox, or chickenpox. So you get these lesions, these sores on your face and your body, and you're sick for a little while, and then it goes away. So actually, chickenpox is a good analogy. So anyhow, so just know these names, and there's a million more, but in all cases, read the textbook on whatever we talk about, but you're only responsible for the stuff we did talk about. I will be skipping a lot of stuff. So if I skip it, you can skip it. And I've always felt it is not important enough to talk about in class, it's not important enough to put onto a midterm. And every so often I kind of get mixed up and I forget. And I'll put something onto a midterm that we did not talk about. And I've always found the students are very good about letting me know about that. So anyhow, so generally if we've talked about it, it's fair game, read the book. And if we did not talk about it, then don't worry about it. Any questions on any of that stuff? Okay. So some examples of